I love coming here. So much of life is about finding your people, and I spent a long time trying to figure out where my people were, and they're here.
I'm very happy to be here. My name is Mike Shah, and you're here for Back to Basics on functions. So this is part of our Back to Basics track, organized by myself and Klaus Ingberger, as well as a software development track. So, we've lined up a great program for you, and I hope you have lots of fun and learn some new things here. So regarding this session, it's about 60 minutes here, and we'll have an introductory level here. So for many of you who are at CppCon, you might know quite a bit about functions here. So I would encourage you to raise your hand at any point, and I'll try to repeat your question. Otherwise, there's a microphone. But if there's a best practice you want to share or something that comes to mind, please feel free to do so. Otherwise, I found it very insightful to just go back to a foundational topic and think about, what are the building blocks of programming? I think this is actually a good exercise, maybe something you could bring back to your teams as well, as far as tech talks, and have something that everybody can get involved with. So just a few ideas there, and I hope you enjoy the Back to Basics, whether you're here with me now or in the future. Alrighty, so getting into it, a little bit about myself here. You can read about, again, done a lot of C++ stuff, and mostly teach these days with occasional C++ work. The code is available for this slideshow if you'd like to take a look. It's already on github.com, so you can revisit when these slides are posted. And of course, you read the abstract that brought this wonderful audience here. So again, thanks for being here. So our goals for today. Well, again, we're going to be doing a tour of functions. Again, from the fundamentals of C++. So again, some of this stuff you folks are going to know quite well. Maybe you'll think about how you learned it or reflect on it a little bit and what you would teach somebody else. So again, a wide audience of things. And if you are an expert and you're sitting in the room, I'll try to trickle in a few little, best practices and things that you might catch as well, just to give you some value. So hopefully it'll be useful and enjoyable for everyone, but I know we'll have fun. So functions, again, where does it all begin? And where does it usually come back to when we visit functions, which we'll get to. But perhaps it's just a term that you learned in your math class. At least that was my first exposure. Maybe 7th or 8th grade if you're in the States, somewhere around there, and you're doing some algebra. And we learned about mathematical functions that look something like this on a graph. All right, so we plot things. We've got this f of x function, the independent variable x here, some dependent variable that we generate to resolve from. Okay, and that's the red line in this graph. And then things also get a little bit more interesting. Maybe you have piecewise functions, which in a way have some sort of condition or conditional behavior. Right? If the value is greater than 0, maybe this particular line here is -1 always, and otherwise it's a parabola. Okay, so with these math functions, this is sort of how we learn things, but in programming languages, I think we also learn this, but we find they're very expressive for what we can do with them. Right? They're some of our fundamental building blocks for building programs. So, thinking about maybe your schooling experience, some of these math expressions or functions that you learn about, of course, the trigonomic ones. These are, of course, available in a programming language like C++ and our standard library or others. So we do have these things available. And we can think about things purely from a mathematical way. In fact, many of you folks might be working in domains where that's what you're doing. So functions in our programming languages, as I mentioned, can express or be the building blocks for lots of exciting different domains and ideas. And again, since we're back to basics here, I have to take you back to my origin story. First sort of learning about functions and their power. And if you reflect back for just a moment on the first time you learned what a function is, or maybe some other construct, I bet it was kind of magical. At least it was for me, and I still do remember it. 20 odd years ago at this point already. But here's where I started my origin with a basic programming language, Dark Basic Pro. And, you have to give some credit to those who led you along the journey. So anyways, a basic programming language like this, designed to build games. It's very exciting, something that might get a younger person into programming. But again, instrumental in my career and learning about many of the things I know about today. And of course, as I mentioned, the first construct I remember learning about is a loop. How instrumental, how cool. This idea that you could repeat work. And I remember explaining this to my dad, who also knew how to program anyways, and was probably bored by it, but wow, you can repeat work, and explaining this idea or just thinking about it. Okay, save yourself time from typing. And of course, a function, also very similar. But I wasn't thinking about it that way. Of course, when I was looking at a standard library, or in this case, a game programming language, I just found a set of functions that were really cool and interesting. Wow, I can do this graphics stuff, or work with images, or play sound files, or whatever. So interesting, common set of functions which I could do something. And loops and functions, again, are sort of related. In fact, they are abstractions themselves. So again, it's just an interesting thing to think about, again, when you go down into the foundations. So again, here's an example. And this will be the last sort of basic code that I show here. But the point showing that there is a family of functions that were collected and could do sort of similar tasks. Loading a bitmap image, loading a specific one, maybe setting the current bitmap or some state to do something interesting. So again, we get used to seeing these things. And we see these in the standard template library, where we have, again, libraries of math functions or other things. So one of the insights from this manual here, again, was this idea that all these functions were grouped together in some sort of common family here. And that made it much more learnable and approachable for me to sort of dive into one topic at a time and just kind of see what was available. Again, it was organized and made sense. Now, the other thing that this manual had, again, 20 odd years ago, was this first line here talking about user-defined functions. And it stated, there will come a time when the ability to create your own functions will be priceless. Wow, okay, that sounds valuable. So, again, another key insight here, I can write my own functions. I don't have to just use the stuff that was given to me. So again, my imagination widens at this point. I can basically do anything I want with a programming language. So now it really is a tool for me. So again, this is the sort of revelation I had along my journey, thinking about functions. And again, as you look back at the fundamentals, it's interesting to think about how your mental model changes. So hopefully I'll be able to take, if you're a total beginner, you to another mental model about how you think about functions. Again, for those of you in the room who know a lot about functions, well, maybe you'll think about how you teach this stuff. So here were a few of the fundamental ideas captured here from this little origin story. Functions are commands that return a value, or 0 or 1 values, I should say. These functions can be grouped in a common set of functions. And of course, it's going to become important that I can create my own functions. And I need to think about how to do that. Okay, so with that in mind, let's go ahead and explore a little bit further into this world. So functions, again, starting from the very basics. There's some sort of abstraction where we can write reusable or modular code, so we can share it with our friends, reuse it in our other projects. And at a minimum, the way to think about them is something that returns a value, okay, at least from a manual. But a language like C++, maybe starting for the very a basic function here, which I have a code snippet on the right here, I can have a function that doesn't take in any parameters at all. So this prompt here that's void, for instance, specifies empty or nothing there. And I do like to specify void, just so it's clear. And then the return type, also void, doesn't return anything. So this is just a function, as we'd call it, but in another language, it's a procedure, right? It's going to execute some block of code for us. Or other languages also call this subroutine. And here's another function here. Well, it's called square. Again, at line 16, it takes in one integer and returns an int as well. So again, this would be an example of a function. Again, this one's specifically a math function that takes in a value and returns one value as well, doing some math computation. Of course, there's other interesting functions that maybe don't take any parameters, like random, number generators, for instance, and just produce a value for you. And then we've also got to think about functions that transform data. That's all our machines are doing at the end of the day. just taking input and transforming it. So maybe we'll think about mutation and some of these things as well. So the anatomy and the components of a function. So some things to think about here. Well, let's take a look at that load bitmap function, but maybe from a C++ viewpoint. So something like this here. And it has different components that make up the actual function that does the work. So our functions need to have a name, and we'll talk about if that has to be unique or not, but at least a name to start with, something with an underscore or alphabetical symbols. And a good name should describe what the function's doing. Loading an image, for example, is fine. We'll talk about maybe how to improve this further. And then we've got the parameters of our function, the inputs into our function, so 0 or more parameters. And this one has exactly one parameter here, a string. And the parameters themselves are part of the definition as well. And the arguments are what we supply into it, just to get those terms completely straight. Now our function also has a return type here. In C++, we can return 0 or 1 values. We saw an example of returning void, which is nothing. But if I specify a return type, something more concrete, like an integer here, that's what we're going to return and produce from this function. So we have the return type and a corresponding return statement here with the result that will be produced from this particular function. And in this case, maybe it's an error code or something indicating we successfully loaded this file. So again, might be a good idea to have. Just a little trivia for folks. Do folks know what the return type of, and this is getting off of C++, but printf is? Is it void? It is an int, yeah. Does anybody check what it is? Count of characters printed? Yeah. Does anybody actually check it in their code? Probably not. I don't think, but depends on what your domain you're in. But anyways, you might want to think about having a return value and using it. We'll talk about what the cost is, though, of course. Now, the other parts of a function here, the function body, is what comes between the curly braces. And this is going to tell us how we're actually achieving whatever this function's doing. Right? This is where you get to do your implementation. Okay, and hopefully you've named your function well, such that if someone's reading this, they understand it loads a bitmap file. And if you implement it, you will, of course, load a bitmap file, okay, for whatever that means. Now, again, how we could improve this function, is it a bitmap file, is a bitmap image file? Again, some different ways you could improve it, because bitmap probably means different things to folks here. Now, the other thing to keep in mind about the function body is the scope here, just like other variables in C++, the curly braces define our scope or where the variable is alive. I'll put in a reminder later about how we think about that, but that's the idea. All right. And finally, the combination of the name of the function and the parameters form what's known the function signature. So this is sort of the unique, again, signature, just like when you autograph something, it should be unique with your name for identifying this function. So that combination of name and the parameters. Okay. And that's the idea here. Now, a little aside, again, because I want to toss in some stuff for folks who might be more advanced sitting in. You can get away sometimes with no return statement. I'll probably get a warning. You probably shouldn't ignore it. But that's just something to keep an eye on. And sometimes even if you're doing a debug build, it'll allow you to move forward. Okay, so don't ignore those warnings. They're probably you probably need to think, is it a void return type or not? So again, enable your warnings on your compiler. And make sure you have a return for every path. All right, so at this point, hopefully we understand the basic pieces of the function or the anatomy here. Again, we've got a return type, the function signature, which is unique, and the function body. Now, of course, these are sort of the basic things that you need. We probably type these in without thinking too much about them at this point, or if you've been doing C++ for a while. But some of these things do become important, like the function signature when you're debugging error messages and trying to figure out when you're linking code together or building a library, what's actually going on. So again, the foundations always come back and matter. Okay, so let's talk about what happens when we use a function. So from a machine standpoint, what happens when we make a function call? So diving a little bit deeper here, let's see what the machine's actually doing here. Because again, a function's a reusable piece of code for us. And I think it's very useful, again, just to understand what's going on here. How many folks use Godbolt or Compiler Explorer here? I've heard of that? Okay, I'm seeing about half the audience. If you haven't, I'm going to show you a few views of it, and there will be links so you can click and play around later. But it's a really nice tool for showing you the actual assembly or machine code so you can understand what's going on in your code. And I'm not asking you at the C++ conference to go learn assembly, but I do think it is a good idea just to understand a little bit and see what your code's doing. So here's the function that we're going to be focusing on. Again, keeping the examples small for today so we can understand what's going on. But an add function, again, looking at the function signature, taking in 2 integers, and then it's got a return type of an int. Okay, simple enough thing that everybody could write. Now, when we make a call to that function, which if I direct you sort of to the left of the slide here, which I'll circle, I've got to add 7.2, so I'm passing in the arguments to that function here. This is at the actual call site here. Means when we're calling a function or using a function, that's what I mean by call site. If I look at the corresponding assembly code, so what your machine sees, that's replaced with the call instruction on this sort of weird looking version of add here. If we sort of ignore the Z3 here and just see add, you could probably interpret the I and the I after makes out integer and integer for the parameters for that function. Again, our function signature. Okay, so if you get interesting linker or compiler errors that look sort of like your function, now you know how to interpret that. Okay, but that's what's going on at the assembly side for the machine. That's what it's calling here. And we'll see the label in a moment here. Now, some other interesting things that are going on here are thinking about, well, what happens to these arguments that we supply into our function? I've got 7 and 2. Well, if I sort of look at our assembly here, at lines 39 and 40 towards the right side of your screen, you can see, and again, it depends on what assembly you're looking at, but I can see the values 2 and 7. And I can see it looks like they're being stored somewhere. These are registers in assembly, which we can sort of think of like variables, but we are moving these values over. And my other tip for using Compiler Explorer doing this is to try to use different values here. You know, the more weird, the better, but probably not 0 or 1, just so they stick out a little bit. So 2 and 7 I can see here clearly, and of course match what's going on. Okay, so if we explore the assembly a little bit more here, what's produced from this function here on the left side is something that looks like this, okay, depending on your assembly that's been generated. We've got that label here, underscore Z3, add II, and a colon. And again, in the assembly, that's sort of a label or an address that we jump to and call our function code. Okay? And then the rest of this has to do with setting up the actual return address so we know where we called this function from and can, after we do add, jump to line 15 and continue our execution, as well as the actual work of this function here. And if you look close enough, you could probably trace through here and see an add instruction and see the value that's returned. Okay, so that's the idea. That's what's going on deep inside the machine here. So, you know, a few takeaways here from the machine viewpoint. You know, and I think this is a good exercise for folks to do, just to again see what's going on step by step. 1, so that you know there's not magic. 2, because it's useful for debugging when you're actually performing debugging or trying to fix an error. But at a minimum, we see that there's some sort of notion of storing a return address, so we know where to jump back from. This notion of copying or otherwise moving arguments around, which is going to be important for us later when we think about how we set up functions. And this idea that every time that I'm calling into this add II or add function, it's building up what's known as a stack frame. Okay, so if you ever got a stack trace or a stack dump or something, this is some of the information that you're getting back when you debug. All right, so we've looked at functions. We've looked at a single function call. And of course, we have recursion available in C++. Some languages don't support it. Some do. C++ does. Right? We can do anything in C++. That's the great thing. So again, this is just a little bit of a review of what we talked about where we're storing our arguments that we pass in the function, the return address, and even our local variables, right? That might be part of what we're doing within the scope of that function. Okay, that's all the allocation going on. Okay, so that's just a little review there. And of course, if you want to look at the recursion, here's a simple example with factorial. The point of this slide is just to show you, yes, we can make recursive function calls, and that's going to build up this stack frame with different parameters. Okay, so that's factorial. What's new here, or what wasn't seen from our basics, is there are two return statements here, line 18 and 20. And again, that's totally fine. Two ways to exit this function, which is useful for setting up your recursive base case and the recursive case. But the important thing being that we do, in fact, return from any possible path. And here it is, just refactoring a little bit better. You'll notice my cout statements here were repeated. We can do better than that. We can write loops. And if we're at CppCon, we can probably write lambdas, which we'll learn about, and for each, and so on. All right. So again, moving through this, we talked about our scope of variables between the curly braces. And again, thinking about things in terms of their lifetime for when they're allocated. So again, you can see the scope of these variables. We can reuse names within the different scopes. Okay, so this is just refresher stuff. And the point of that is, well, you can reuse names in parameters of functions, as well as have them elsewhere in your program. Right, to the compiler, at the end of the day, when you look at things at the assembly view, it's all just numbers and transforming data. Okay, so moving beyond that, let's try to do something a little bit more useful with our functions, right? We said there are these modular code blocks that we can work with, but let's try to understand just a little bit about how they're organized so that we could, again, maybe build our own game programming library or whatever functionality that you're interested in. So because we looked at this previously with our little add example, and this is an example from Compiler Explorer, on the right, the assembly code, we can see that this add function, it is part of our code, right? It is stored in the text segment of our actual program that we compile. And that's kind of interesting because, well, we can take an address of a function and maybe do some other interesting stuff, right? It must live somewhere, right? That is code that we have. So let's start thinking about this in pieces here. Now, the first thing to think about with our functions, if we're going to kind of build these up, is that, well, we need to have some sort of function declaration. And in this particular example, what I'm showing at line 4 and 5 is just the function declaration. You'll see that it's add here, 2 parameters, and you'll notice you don't have to put int a or int b here. I can actually just put the type. I would recommend probably putting a name there. That's probably some useful documentation. But again, that's just the signature of the function with the return type. Okay? And as long as I have that there, when we call this a forward declaration, then I can, in my program anywhere after, like at line 11, make a call to that add function. Okay, and I can do this so long as later on I actually do have a definition. So towards the lower end of the screen, you'll see I provide the body of that function, return a plus b. Okay, and this is because C++ parses things from top to bottom. So we need to see that something exists or have some promise that it exists, and then parsed top to bottom. Okay, so when C++ sees this at 11, it says, yeah, I know what that is. I can replace that with that call to add, like we saw in the assembly. Okay, so the forward declaration is just a promise to the compiler and or the linker that, yeah, everything's going to be fine. Trust us. Okay, so with this idea, rather than just sort of putting everything into our one file like this, we can start organizing our code into a library. Okay, so to the right, what I'm going to reveal to you is the different pieces of how we built a library of functions. So the first snippet here is just a file called add.hpp or add.h if you prefer, but a header file containing our declarations. Okay, and this header file is sort of our interface that you would give to a friend and say, here's what's available in my library. And here's what this function is. Okay, the signature and the return types. And then I'll have a add.cpp file, which provides the actual definition for that function. And again, this is the implementation in the separate.cpp file. And then finally, rewriting one of our simple programs here. I've got a cout, add, and then taking in the two arguments 7 and 2, and we're good to go. Now the important part also to see is, as far as using this library, and I'll see it at this bottom snippet at line 4, that I've included the add.hpp file here. Okay, and again, include statements. What the compiler is essentially doing is just copying and pasting what it sees from this add.hpp at the very top of our screen and providing that forward declaration, that promise that, yeah, this function is valid. We promise we'll provide an implementation somewhere. And we'll compile in that implementation add.cpp. Okay, so that's the idea here. And you can see how at the very bottom of the screen, I'm compiling the C++ files. The other final note here is that I've included pragma once here on my header file to make sure that since it includes a copy and paste, I only want to copy and paste that declaration one time. If I have it included twice, you'll get a multiple duplication error or something in your message, error messages. All right, so this is effectively our first tiny little library here of functions. And of course, we can start adding more interesting things here. And of course, the purpose of doing this is, well, once I write this function once, and again, you can pretend this is something more interesting than add, if you will. But I can reuse this for my other projects. I can also hide my implementation details in the C++ file. Right? You only have to give your friends the header file in that sense, and then you can compile the C++ if you need. This might open up opportunities for speeding up compilation. Right? I can compile these files in parallel. And again, if I separate out my files, I can break up my source code into just the components that I need. So, tomorrow, if I don't need anything related to math in some project I start, I don't need to include this add library here. Simple as that. All right, and here's the example of just compiling these files separately. If you've ever explored make files or build systems, you'll probably see, something like this, compiling each of the files separately. Now again, I want to take just a brief tiny detour here, taking a deeper look at what's going on, keep my advanced folks curious and my other folks also curious about what's going on here and taking a little bit of a deeper look here. But there are interesting tools where you can do some introspection where, well, if you compile that add file into an object file and actually look at it using some inspection tool, this one's called objdump, but there's many. There's OTool for Mac and others for Windows and so on. You'll actually see there is something, with that funny mangled name, add II, with a Z3 and underscore on it. And if you interpret it, you'll see a capital F here for a function and a G here. So it's a globally available function. Right? I include this library and it's available for me to use, add anywhere. Okay, so that's just something kind of neat here. You could bookmark this slide and revisit it later. I think it's also just useful to see as a debugging tool when you build libraries what's going on. Now, another thing on this brief detour here is you can actually add static in front of your C++ functions, both the declaration and the definition here. And if we do that same inspection with that objdump tool, well, something changed. And it's so subtle, I've highlighted it to save us time here. But now we see an L here, which was different from the G, meaning this is locally available. Okay, so static's sort of a way to hide within a compile file and say, well, this add function is actually only available inside of my add.cpp library. Okay, and the idea there is you might have helper functions or other things that you don't want to expose to some users. So this is a way of information hiding. Again, you might think about utilizing. And you can see all the fun compiler errors that you get here. But they're not things for you to be afraid of because, again, you'll understand why you're getting these. Okay, So we've got a function, we're starting to build some libraries, and I want to add more. So how do I group related functions together to build something more useful, more powerful, or even composable? Because again, well, we're going to probably need more than add, so why not subtract, multiply, divide, etc. A few other function ideas here. So they're all in this math.hpp file. Again, grouping them together in my interface here. And so this is one way to, again, group them together in this header file. And again, they're implementations in the C++ file you can see here. Again, they're crammed together so it can fit in a slide. But logically, when I organize these, here's another strategy. And this is sort of a C-like strategy, but we want to graduate, right? We're in CppCon. But you could, and this is common, you might see this, but maybe prefix it with a module name, math_add, right? These are all related. Maybe they're working with the same type. It's not terrible, you're at least showing some relationship. But again, in C++, we probably want to group these a little bit more logically in a namespace. Okay, so a namespace, what it is, well, I'm sure everyone here has used standard : or stood : however you prefer to pronounce it, cout or something. That's the namespace for the standard library. And of course, you could have nested namespaces and so on. At line 5 of this top image, I've just used Mike here. And I can wrap these functions as needed here. My header file actually is at the bottom here at the declarations. I can see that this namespace, so I don't have to type out Mike : every time, is below here. Okay, so I usually like wrapping them in those blocks. But again, you can use the scope operator : if you prefer to just do Mike : multiply for whatever reason. And again, if these namespaces get really long, like if you've got the Mike, math, 2023, etc., library, you can use using namespace Mike : CppCon : 2023, whatever. Though I do recommend just using that at a local scope. Versus just putting, using namespace at the very top of your files. And again, the point of that is to show the togetherness, grouping the functions, as well as avoid naming collisions, because that's likely someone else has written an add or subtract, function somewhere. All right, so here's the full example if you like and want to play around with the code later. So again, I'm not an expert, newer things coming. Compilers are supporting modules, another logical way that you can start grouping together and building your libraries. So you might start hearing this term pop up more and more. But again, this is a way to sort of put together in one file a module. I'm still learning about these in C++. I've used them in other languages. But again, these work quite nice in that you can effectively put together one function and then rather than explicitly hiding something, you can explicitly just export out the actual functions you want users to have available. Okay, and soon we'll start using import. So that's just something you might want to keep an eye on. You might see on other people's slides here at CppCon. Modules are available in C++ 20. Okay, so thinking about other ways to group functions together, of course, we've got namespaces, and those are sort of our free functions in the sense that they're independent, if anything. We can also group functions together in everybody's, I don't want to say favorite, but everybody's paradigm that maybe they learn in school, object-oriented programming. Okay, so a way to group together actions with attributes, if you will. But this idea here is, maybe we've got, again, some series of functions and they need to work with a common set of state or variables. So you create a type for that. In this case, a class or a struct. So I'll draw your attention to the top right of this screen, just as an example. I've got this class here called an image. Make it a class or a struct depending on public or private. And I've got at least one member function here for loading an image. Maybe changing some pixels on the image or converting it. You can imagine a bunch of different member functions here, and some common data associated with our images. A file name, extension, so on. So again, these are our functions, but specifically when they're within a class, within that scope, we call them member functions, Other languages call them methods. You'll probably be forgiven if you mix them up, but I tend to see member functions in most of the documentation for C++. So that's the idea there. And then your actual implementation, if you look at this middle block of code where my laser pointer is circling, you'll see, again, image, the scope operator, so at that class scope, and I provide my implementation for this load image here, okay, and an example usage, okay. So that's one way we can, again, group our functions together, if you prefer, or if the object-oriented style is the right way to tackle a problem. Now, this starts to get a little bit interesting when it comes to functions because with object-oriented style programming, we can do stuff like derive a new class from some base class. So I have this class here called image, for instance. Well, I might decide I actually want to create something, which I've done here at line 14, called bitmap. Okay, so it's going to be like an image. It is an image, right? It's inherited from it. And I want it to have the same functionality for loading, but again, the code routine is going to be a little bit specific to whatever bitmap data format is. Okay, so we've got to implement that ourselves. So in C++, when this happens, or when we use inheritance, and if I want a different implementation of that function, well, I can mark the base class function here at line 5 virtual. And that's basically an instruction to the compiler that says, hey, this member function here might be overridden and a new behavior derived, okay? Which we did do at line 16. You can see I've marked it override. You don't have to, but you should. It's good documentation to the user. It'll also catch other little errors, like if I misspell load image or something, it'll say, hey, I don't find anything I can override in the class above me. But that's just, again, a good practice. But anyways, you can see down here on this bottom snippet, lines 8 through 10, I'm overriding that behavior, okay, and just showing its bitmap : load image. So this is the idea of what happens when you're using inheritance. And this is always a good interview question, I think, for folks, or at least I've been asked it. My students tell me they've been asked it on what's a v-table? But the idea is, again, how we're implementing. One way to implement this particular behavior, not the only way, I suppose, is that, again, when you have this virtual member function in your class, as soon as you have one, there's going to be a table of functions somewhere keeping track of, well, which implementation of load image am I actually calling? Is it my is it the base class, the derived class, or something else? So again, you can just kind of see here every class or struct is going to have its list of functions and a table that points to the appropriate function to call. Okay, so that's the idea here. So, this is a back to basics talks on functions. There's been many, and including at this CppCon, there will be more discussion at back to basics on object-oriented programming. But a few places we can take this further with pure virtual functions. That's how we do interfaces in C++. Friend functions, other ways to access shared state, and other things like static member functions for sharing within some data type. So I'd encourage you to look for those for the proper hour-long treatment. Okay, so we've got a way to, again, create our functions, build some libraries, maybe group them together. But again, functions are our fundamental building blocks. So what makes them powerful? And this is what we think of, from maybe a mathematics standpoint, again, circling all the way back, is that our functions are composable building blocks. So what do I mean when something composes? Well, let me just point you to this line 17 here. And it's a little bit of a silly example. It's a little bit maybe silly to read too. But I have here an add function. It's going to store in some result or accumulate it. And then I have this multiplication function that's taking in 2 arguments here. Okay, it's kind of interesting. It's computing something called the dot product. But what's sort of interesting about this is that I'm taking the input, which is the result of multiply, as my input to this add function. Okay, so I'm composing or sort of building up some functionality here, okay, and computing a result. Now, is this the way I'd write dot product? Probably not. I'll show you in another slide something a little bit cleaner. But the point being that we can compose, if I have add and multiply, these are useful functions. And again, you could just say, well, Mike, just use the plus and multiply operators, again, which is probably what I do. But again, if you've gone through the trouble of writing add and multiply, maybe those functions are doing something useful, like checking for integer overflow or other error conditions, or just logging on your call stack what's actually going on. So again, there's always uses for these things and some power. So let's rewrite that dot product just a little bit more simply here. And again, basically what the dot product was doing there is doing 3 multiplications for each of the 0th, 1st, and 2nd inputs from these vectors, and then summing them up. Okay. So I could kind of rewrite this. I know there's going to be exactly 3. This is just a little bit cleaner, and it's fine here. And I know there's a million ways to rewrite this using SIMD instructions or Verilog templates and so on that are kind of fun next steps after today. But anyways, just with observing these building blocks, something kind of interesting starts emerges by keeping this very simple and composing things with these really tiny functions. Again, multiply, add, keeping them sort of short and simple here. And usually when I'm programming and I do something simple like this exercise and I break things into these nice modular components, you might discover other behavior that's kind of interesting here. Because if I know the size and the type and some of these attributes here, we could actually compute this function at compile time. So C++ allows us to perform computation while we're compiling our code, so we don't have to do it while we're running. And that's really great. It saves our users time. We pay little cost for the compile time, but we want our users to win and have a good experience. So C++ introduced Const Expert. And it's introduced it in a number of ways. I'm going to talk about Const Expert functions. I know there's other, Const Expert variables and all sorts of other stuff. But this is basically the way to compute at compile time. And here's sort of the simple canonical example here, where I have our beloved square function, again, another math function. It's taking in some input, and we qualify a return type with Const Expert. And that's a suggestion to the compiler. It's not a promise, right? We don't have that strong of a guarantee necessarily, but it's a suggestion that says, well, I think if we provide some value that's known at compile time here, that we can actually compute this at compile time and just store that result. Okay, so that's the idea. So let's look at that with this, dot product, a little bit more of an interesting example, and actually just mark it as Const Expert. So here's the compiler explorer version of it. What I mostly want you to take away here is just on line 13. And again, I know it's a little bit tiny, but it says Const Expert int there in front of our dot product. And in fact, I've marked pretty much everything const as much as possible. Because if it's const, I know it's not changing, and then I can compute things at compile time. So that's a huge win for our users, again, saving computation. So again, the point here is then, well, my little building blocks, maybe those could also be Const Expert, right? Maybe I can suggest and make the inputs also const, so non-changing, and always be able to use those as well. So again, by breaking things into these tiny pieces, it's usually easier to see that this might be possible. Okay. And for this particular example, there are some other core guidelines about Const Expert I've linked in here. But it's essentially just inline these functions. And if we look very carefully, it's going to be too small for those of you in the back row. But you'll just have to believe me that my hexadecimal number reading capabilities, this says 1C here, which is the value 28 that is computed from this particular problem. So there's no add function call there, just simply figured out, yep, that's the value, just plug it in there, and that's it, okay? And no work's being done. And this is a phenomenal thing, I think, in programming or languages that allow you to think at compile time and at runtime as well. So that's a major advantage we have being a compiled language, in my opinion. This compile time function execution possibility. Now again, this also, just to again give some more ideas about how we might want to write our functions and think about them, now that we know about things like Const Expert, is trying to write our functions in a pure, again, coming back to our roots, right? Those math functions that we learned. One input generates the same output. And we call those pure functions, okay? If that's truly the case, that if I pass in constant values that are the same input, I'll get the same value out. And there's all sorts of neat powers that you can do with this. You can cache those values and so on. And there's different classes of function purity, like very strong, like in this case, everything's const, or maybe weakly pure. Maybe there could be, some side effect in a parameter or something. But again, just a few things there. And just for those looking forward, C++ 23 and I believe 26, which I was looking at CPP reference, I think most of our math functions will become Const Expert then, or many of the ones that can will. If they haven't, probably a low-hanging fruit to write a paper and get your name on the scoreboard there. So, thinking about our function parameters a little bit, thinking about const and Const Expert, just a quick review of some of these things, because we've been looking at functions from sort of this mathematical input, get output view here. But again, in C++, we can pass things by value and pass by reference. Okay, so what does that mean? I think I can actually ask my folks to think about this for half a second. Might be online folks can pause. But yeah, what's the value of x going to be? I'll let you, just think about it in your head. But we've got int x equals 9. Call this function here. And if you've got this memorized, I don't want you to necessarily, memorize. I want you to think back to that assembly. What was going on in that assembly code? And this is where it's useful to go into Compiler Explorer. Again, you've probably been taught the answer. But again, to think about, well, actually the answer is, I pass in x, I seem to do something with that argument here. But of course, as we know, it is not mutated when we print this out after the function. What we're actually mutating is the copy, okay? And we got to see that, again, in our early slides, thinking about the assembly view, where we were moving a value, which, maybe they could be called like copy a value or something. But that's the idea here. Okay, we're modifying the copy in the function within that scope. Okay, so that's why we had to make sure our fundamentals about scope we were clear on. This idea of pass by value or pass by copy value, which I learned from Walter Brown, another name for this, is what we're doing. We're actually modifying this value. And just as an experiment, it's useful sometimes to just play around with some of the tools you know about, like the ampersand operator. Again, you can think about all of your operators today as functions. That's what we're talking about. So the ampersand function, which returns the address of some symbol, like a variable or a function. The idea here is, again, just play around with this a little bit in your functions and just print out the address of x. You will see that it's different. Okay, and I can refer to other Back to Basics talks on pointers and these types of things. Okay, so the other ideas here is instead we can pass by reference into our functions with the ampersand here. So this is a reference here. Now, what do we want to do here? Or why do we want to do there? What do we want to do this for? I skipped your exercise, but hopefully you get the point here. I think this audience will be okay. We are actually modifying the actual value. We're passing in a reference or referring to this as an alias, by some other name in this function. So there is actually a mutation going on here. So this is the other part about functions when we're designing our libraries here. Maybe I'll give our audience a chance. Why would I want to do this? Pass by reference into a function. What's a canonical use case? Just shout it out if you've heard or learned something. Has anybody? Yeah, cheaper if the value is big. Yeah, that's almost exactly why. Because we've got to do some work copying, right? That could be expensive. So, a couple reasons. I mean, you might actually want to modify. Maybe this is a function called set value to 9999, and that's exactly what it's doing. But reason number 2 is the big one, right? You want to avoid making the copy. Think at scale. If you've got 10 million elements, whatever big means to you in your domain, that's an expensive copy to make. You also get a little bit of safety passing by reference. It's a little bit harder, right? This shouldn't ever be easily a null value. I guess I'll say it that way. So you get a little bit of protection there, and you don't have to check necessarily that that's a null value or some of these little things. So it's useful to pass things by reference. And again, we don't want to throw away our other stuff that we learned. You could pass things by const if you don't want them to actually change. And again, you get that performance boost. Okay, so we've learned, again, why to do this. Now, there's some other tips here, again, just for folks to look forward to about thinking about how you're passing things along. Instead of by reference, if you want to modify things, you can also pass things by pointer. So I call this pass by pointer. It's the same as passing a copy. But again, a pointer holds an address, so you can sort of indirectly access some shared memory. So that's the common pattern in C that you can do. The tricky thing is, if I'm looking at line 5 here on the right side of my diagram, I've got this array here, which is an integer pointer to an array, and I've got to pass the size here. Much better if we can do what's at line 11 here. And in C++20, you can use something called a span, which is holds a pointer and the length effectively. Okay, it's one parameter. Harder to make mistakes as far as mismatching the size. So again, that's a nice thing to use. Okay, and relatively efficient as well. Okay, so some more things with functions here. If I want to write a lot of functions, we've got we've got our ways to group them, but sometimes we want functions to take different parameter types. So in this example, I've got our square function, and maybe we don't want to just operate on integers, right? We want to operate on floats. In C++, we can reuse our names, which is great, meaning square can be reused, but we can change that function signature from taking in an int parameter and taking in a float parameter. Okay, and this will work. This compiles great in C++. And we don't have to keep track of many different versions of functions. Okay, so this is a type of polymorphism. And there are some rules about which function will actually be called. So you can look at, again, this is for reference for you to look back on in however many days or weeks or whatever, argument dependent lookup, which helps you determine which function you're going to call, maybe based on the types, maybe based off of the scope. So here's the list of rules to keep an eye on. Now we also have function overloads. So maybe I don't want just the square, the single parameter to change, but maybe there's going to be multiple parameters, right? Maybe I've got a really safe version that checks some condition or something. So again, same rule applies. You can use the same function named square and just add multiple parameters. So no problem there. Now with this, if you start adding lots and lots of parameters, we have to be a little bit careful. I'll try to show a tip later if we have some time here. But you can make the parameters default values starting from the last parameter. Right? They sort of have to go in order for the common use case. And I would recommend doing this, right? If you've got a small example like this, for instance, and there's probably some ways you'd want to compile this out. Again, my template folks will know. But this is just something you can, again, do with your code so you don't have to maintain as many implementations as square as possible. In this case, it's just these two. Okay, so refer to that on templates and back to basics. Now, we've got other interesting things we can do with our functions regarding their state, as far as how we're keeping track of maybe what's going on or between different invocations of functions. So with that, I'm going to introduce two things, one which we've seen, or at least two things. Static, again. Now we saw this with our functions, something about making them sort of hidden. But if I use static within a function, it keeps this variable, counter, which will be shared within each invocation of this function here. Okay, so we can see that in the top right. But what's also an interesting thing that we can do is we can create what's known as a function object. These have the fun name of functor, which we can see the state that's sort of within our class or our struct here. Okay, and basically what we're doing is we're overloading, so that thing that we learned about here, operator parens here, so we can use this object that I've declared at line 19 like a function. Okay, and it's going to do the function call here and maybe keep track of a state. So it's sort of like that static thing with a function, but again, I'm encapsulating that state a little bit closer or as I need. It's per object now, right, versus the global function lifetime. Now, what's neat about functors is that these actually have evolved into something else useful in C++. Does anybody know? Yeah, go ahead. Lambdas, yeah. So this example I'm going through because we're a little short on time, but it's going to be the exact same thing as what I'm showing here. We can declare little what are called unnamed functions, referred to as lambdas. They look a little bit weird, and I usually assign them with a auto variable, so I can just have this print v. But I've got, well, any state that I'm capturing, and that might be from outside or maybe local state. The parameters, and then whatever work I'm doing here. And I can divide up my functions now into little building blocks local to it. Okay, so that's another nice thing that we can do. Now, if you are going to use this lambda more than once, then you can give it a name, then you can make it a proper function and think about its visibility. So just as a general rule of thumb. Lambdas also open up the door for more interesting stuff here. Again, you can take a look here, but this idea that, well, now that I've got these little compact things, whether we want to think about them as functors or lambdas, I mean, can we just pass functions around? That sounds kind of interesting and fun. And we can in C++. And this is getting towards higher order functions. And what I'll say about this, I'll get into an example here, is we can store a function because, again, it has an address somewhere. Okay, and our tools for this are, again, C-style function pointers, or modern C++, we have a std or standard function here, with that function signature as the argument. Int being the parameters, and int, which is the return type. Okay, so in this little example, I've just got a function here that holds some operation like add or multiply. Right? It can hold things with that same signature. Okay, so that's the idea here. So, there's some more examples here, but the idea again is that at line 12 here, I can now pass around a std function as a parameter, and that can change the behavior of my functions. So again, this is a way to make our programs a little bit more dynamic in the actual operations that they're performing. Okay, so higher order functions, again, super powerful, and again, making us think about how we compose our programs. Now, something else that's kind of neat is if I can encapsulate and hold a function, right, and pass it as a parameter, again, it's just some location in memory. So you could store those functions in tables, in data structures, in event queues or whatever. And that can be very useful for testing purposes, automating things, right, if you want a series of functions to be called. So again, the purpose of this slide is just to show you I have this array here of two operations that can be things that take in integers, return in integers, and I've assigned them to add and multiply. And I can just call my operations here in a loop. Okay, so nice for testability or driving your program, essentially. So we're nearly at the end of our tour here. But of course, our journey with functions doesn't end, right? We've touched on a lot of different things, right? From the basics to, whoa, we jumped to lambdas, those sound cool, in higher order functions and some different things. So I'd encourage you to check out those other Back to Basics talks happening now or the ones that have previously happened. Again, think about or rethink about the foundations of functions. There's all sorts of interesting things like function templates, testing them, remote procedure calls, etc. And did I mention coroutines are new and exciting? Then we start thinking about how our program's controlled with functions. Okay. So for the purpose of our last 30 seconds, and I'll hang around for questions as well, I'm just going to flip through some tips here. Name your functions well. Here's a few examples. The more descriptive, the better, right? We have plenty of memory to do that. Describe the action. Functions typically should have one job. And you can look at the standard library. This is maybe a hot thing to debate, but it makes them more testable, I think, and more composable. That's my view on it. You can take a look at the core guidelines. Shorter functions are better. This is totally arbitrary. I learned 50 lines. I've seen perfectly fine functions 1,000 lines long. Use your best judgment. Talk about it with your team, but try not to have too many jobs in that function. Okay, it's an arbitrary number, but shorter, usually better from my personal experience. And test your functions, right? If they're small and have one job, it's easier to use them. And you can also use those, use functions as contracts, right? Pre and post conditions for testing behavior, right? We saw a tiny little bit example of that with the square function where we might have, wanted to test some condition, but just a few things to think about that. All right, so with that said, one last one. If you're gonna pass parameters to your functions, lots of things or return lots of things, consider it like an options struct. And if you need to maintain compatibility with older or newer versions, you can pass in a pointer. That'll always be 8 bytes, right? So anyways, those are my hot takes, I suppose. So thanks for coming to the Back to Basics here on functions. All the lessons are going to keep building for this track, so I hope you enjoyed it, have fun. I'll hang around for questions if there's time or energy for that.
Excuse me.
Sure.
On your last page about passing a lot of information to one function, you have one example passing the structure variable one to pass the pointer.
Mm-hmm.
So would you please talk about passing a constant reference of that the struct? What's the difference? Is there any benefit doing that?
I would probably, the pointer I know is going to be on a 64-bit architecture, 8 bytes. So I always know that. If I pass it by reference, references behind the scenes are just effectively like a const pointer. There probably isn't any difference. It's just about the mutation and if you want to be able to change what this points to for some reason. So if I want to change this option struct within the function, then I would pass it by reference because I can do anything. This also tends to be like a C style pattern too, which, I realize I said like use span and so on. But I tend to be using this when I work with C code. That way I know when I'm building a library, it'll work anywhere if I just pass the pointer.
Okay, thanks.
Yeah, thank you.
All right, so with a lambda, what happens at the assembly level? Is it similar to an inline where it just the instructions get added in place, or is there something else happening?
It's pretty similar. So, the place to start looking is with I would start with a class looking at it or a functor. Essentially what happens, I should back up. The lambda is translated effectively to a functor. And then a functor itself is just a class. So if we look at what happens to a class, we've still got the freestanding functions. It's just that our compiler is the thing that's enforcing the rules for what function we can call. So there's really not too much interesting or different. You'll see the Mangle names will be more interesting because they should have the namespace that they're nested in. I'm trying to think if there's anything else interesting. But yeah, you can look at either of the samples. Yeah.
All right, thanks.
Thank you.
Hey, so you talked about like a span for a container and stuff like that. Mm-hmm. Is there an advantage to doing that over just passing a reference, or is it just when it can be null?
If I just pass like a reference to like a vector or something. I would say I usually, for span, a contiguous data type. So for me, that's usually been std array. Mm-hmm. And that's the standard one in C++11. The advantage I get is because it has a size with it, I don't need a bunch of templates with like std array that's 3 elements or 5 or something. It's always just pointer plus length. Mm-hmm. I wonder too, this is something I don't know too much about, but with different string types or something, although string should be kind of encapsulated itself, right? We have string view for this. But I guess same or similar idea. If I have just a vector, I'm just passing a vector reference in. Yeah.
Thank you.
All right. Thank you so much, folks. I'll be around the rest of the conference, so see ya.